Factoring trinomials. There's a lot that could crop up here. There are a lot of different options depending on if your leading coefficient is a 1 or if it's not a 1. And if it's not a 1, then you end up with some different methodologies. So this one's going to be pretty long. But I think there are some kind of general helpful ideas that go along with this, because this is one of those things where for a lot of people it's like there's no middle ground, where either this is something that you're comfortable with or it's something that you're really not comfortable with. So I guess if you're really comfortable with it already, then I don't know what this video is really going to do for you. But if you're not, then I'm going to try to bring in just kind of the things that I think about to try to minimize how long these are. Because that's one thing with factoring trinomials, is it can be really long. So if you're doing it by trial and error, and basically if you get unlucky, it can really drag out. But we'll see what we can do to kind of shorten that up generally. So first of all, a quadratic polynomial is one where the degree is 2. So more specifically, a quadratic trinomial is one where you have a term of degree 1 and a term of degree 0 as well, right? So that way you get 3 terms. We will have quadratic polynomials that aren't trinomials that show up in the next section, but we're not going to have any here. So the first natural way to start is if the coefficient of the leading term is a 1. So notice how the x squared doesn't have an a here. So if you want to think of it as just a is 1 in that case, that's what's going on, because these are going to be more straightforward than if the leading coefficient's not 1. So what you have to do essentially is you have to kind of think of the possible pairs of factors of this c, this constant out here, and you want to find the pair of factors where when you add them together, you get b. And if you get that, then you can factor the trinomial. So in other words, and this is the terminology the book uses, you want to find integers m and n where when you multiply them together, you get c, and when you add them together, you get b. And once you find those, then you can rewrite the trinomial as x plus m times x plus n. And this note, which will crop up relatively soon, although not in the first example, it is possible for the trinomial not to factor. Right? It doesn't have to factor. You can have ones that don't. And when they don't, they're called prime. So something that can't be factored any further, that's what it would be called. And that will show up in a little bit, but it won't be in this first example. Okay, so sometimes, and especially if you're used to doing this, sometimes with these you can see it right away what the factorization is going to be. But I'm going to work under the assumption of if you see this thing and it's not one where you can see it right off the bat. So one thing that helps, and this is where I would start if I didn't see it right away, I would start with the sign of the constant term. Because if you kind of think about what would have to happen with your binomials, so eventually this is what you're supposed to get, right? You're supposed to get 2 binomials multiplied together, the x plus m times x plus n. Okay, well, if that's what you're going to end up with, if you multiplied them back out and got this thing, how could you get a plus 6? Or really, first of all, how could you get a positive number? So yeah, specifically it's a positive 6. But if you just want to think, okay, this constant down here is a positive, how do you get a positive when you multiply these two together? Because what you would do to multiply these out is you'd FOIL them, right? So you'd have x squared from the first terms, then nx, and then mx, and then m times n. So the constant at the end is just going to be m times n. So to get that to be positive, they'd have to be the same sign, right? If m and n are both positive, you get a positive when you multiply them together. If they're both negative, you get a positive when you multiply them together. So the first thing I would notice here, and I guess I should turn the pen on if I'm thinking about writing stuff, but that plus 6, what that's telling me is that m and n have the same sign. So either they're both positive or they're both negative, right? But then if you look at the middle term, that's positive. Okay, well, then m and n must be positive, because if they were both negative, then when you FOILed, you would get a negative coefficient for the x, right? You would have to, right? You'd have some negative times x plus some other negative times x. You'd have to get a negative. So that can't work. They've both got to be positive. So because this is also positive, now we know that not only are they going to have the same sign, we know that m and n are both positive. Because then when you think of the possible pairs of factors of x, or of 6, pairs, there I was missing the I, the only ones that you'd have to worry about would be, well, 3 times 2 would work, right? Because those are both positive, right? 6 times 1 would work, and that's it, right? Because your other options would be, I guess I can write these kind of way off to the side, -3 and -2, when you multiply you get 6, but you're not going to get the right middle term, right? You'd get a negative middle term, so that doesn't work. And then -6 and -1, same thing. You don't really have to worry about that either. Then going back over here, if you add these together, you're going to get 5. So that doesn't work. But if you add these together, you're going to get 7. That's what we want. So that's the one right there. So if we're going to factor this thing, I guess I'll have to move this over slightly so I have enough room. It's going to be x plus 6 times x plus 1. And that's the answer, right? So from the plus 6, we said, got to have the same sign. But then with a positive middle term, that means they both have to be positive. So then the only pairs of factors of 6 that are positive are 3 and 2, and 6 and 1. And then we just have to pick the one that adds up correctly to 7. So that's the 6 and 1. And that's pretty much it. Then number 2 is a little bit different because now the constant is negative. But then we can adjust to that too, because then you say, okay, that should be a minus, not a plus. So that minus 20 that's at the end, if you're getting a negative, that would mean that m and n would have to be different signs, right? Because if I just scroll back up to where it is, because we can't see it right now. So this thing right here, once again, I just want to kind of refer to that. When you FOIL that out, where you would get the constant in the trinomials for multiplying m and n together. So for that product to be negative, one of m and n is positive and the other one's negative, right? It's either a positive times a negative or a negative times a positive, because you know you have to get a negative for the product. So if you're getting a negative constant down here, that means that m and n have opposite signs. So one's positive, one's negative. And then, okay, what does the plus 8x mean? Well, that just means that the positive must have a larger absolute value. It's got to be farther away from 0, because then when you add, if you're adding a positive and negative together and ending up with a positive, then the positive must have been farther away from 0 to begin with. If it wasn't, you would have gotten a negative. So that means that the positive has, I think of it in terms of absolute value, but if you want to think of it as being farther away from 0, that's the same idea. So positive has a larger absolute value. That's the way I think about that. And then we can go through our possible pairs. All right, so pairs of factors of -20 where the positive has a larger absolute value. Okay, well, you could have 20 and -1. You could have 10 and -2. You could have 5 and -4. And I think that's pretty much it. But then when you add them together, you've got to get 8. So the correct one is that one, right? 10 plus -2 is 8. This one's way too big, it's 19. This one's too small, it's 1. So you want this. So when you factor this thing, it's going to be x plus 10 times x minus 2. And there we go. There it is, factored. All right. How about now if you have negative constant, and negative coefficient of the x. This actually isn't that different from 2. The only thing that's going to be different is now, since this is negative, I'm going to have something where it kind of looks like this part, but it's going to say negative x. Negative has the larger absolute value, right? That's how I'm going to think about that. So I guess first of all, I'm going to say, look at that negative 56. That means that m and n have opposite signs. I guess I can kind of start abbreviating here. So I'll just put op for opposite. And then the negative x, or negative 1x, if you want to write it like that. So that would mean that the negative has the larger absolute value, right? If you're adding a negative and a positive together and getting a negative, then of the two original numbers, the negative must have been farther away from 0. So bigger absolute value. Okay, well then what are our pairs going to be? Let's see. Well, we could have that one, which I think would be the kind of the obvious one, which clearly is right. You know, if you add those together, you're going to get negative 1. Are there other options here? I guess so. Negative 28 and 2 would be a pair, but you're not going to get the right middle term, right? You're going to get a negative 26 instead of a negative 1. I guess technically this is a possibility, but it's obviously wrong. Right, you're going to get a negative 55. Is there anything else that even multiplies out? Oh yeah, negative 14 and 4. That doesn't work, right? That's negative 10. So yeah, you want this, the negative 8 and the positive 7, right? So then we're going to factor this out, and we'd say x minus 8 times x plus 7. And there we go. And I guess, you know, when you're writing these out, like if you're going to kind of follow what I do, which you don't have to. I mean, the thing that works for me isn't going to be the thing that works for everybody. But if you were following what I'm doing, like this part out here is totally redundant, right? If you get it in one shot, just go, right? You got it, you're good to go. You don't have to write every other possibility out that doesn't work. I'm just kind of doing this for effect, at least here, right? Because I think naturally when somebody says, what two numbers do you multiply together to get 56? Most people are going to think 8 and 7, right? Just from multiplication tables. Like, maybe somebody's going to think like 56 and 1 first. I could understand that. But most people, I think, are just going to go right to the 8 and the 7 and be like, haha. And then, yeah, you can just go right from there. All right, number 4. Let's see. Again with the negative constant at the end. So negative 35, that's going to mean that we should have opposite signs, right? But then 3x. So that would mean, since that's positive, right, it's a plus 3x, that the positive has the larger absolute value. Okay, fine. Then think about pairs of factors of negative 35. There aren't a ton, because 35 actually doesn't have a lot of factors, right? It's 1 and 35, and then 5 and 7, and that's really it. So you go, okay, well, they got to be opposite signs with the positive having the larger absolute value. So maybe 7 and negative 5. You add those together, you get 2, almost, but not 3, so that doesn't work. And then the other option clearly doesn't work, right? Because it's 35 and negative 1. And you go, that adds up to 34, not 3. That doesn't work either. So nothing works. So what's going on here? Well, this is the situation where it can't be factored. So this, I'm going to do this in a different color just for fun. This cannot be factored. And so that means that it is prime. And I think on the homework, on every single problem, they give you that option where it's either, you have to pick one of two choices, where one of them is you write out the factorization, the other one is that you say that it's prime. I think that's there in every single problem, but I want to say that it only shows up like once where it's actually prime. Maybe twice, but I think it's once. All right, so that one didn't work. What about this? When you have that negative, right? You have a negative x squared. Well, what you do there conventionally is that you factor the negative 1 out. So to do the factoring, you want to have a positive leading coefficient. So you can factor that negative out, or I guess you could look at it as factoring out a -1, which is kind of the way that I think about this. So if you factor out a negative or -1, that's just going to flip all the signs, right? Just like when you distribute a -1, like when you're multiplying, that just flips all the signs around. Same thing when you pull it back out. So then you'd have -1 times x squared minus 6x plus 5. Right? And then for the thing that's inside the parentheses, so for that thing, you have a plus 5 on the end. So that means that your m and n must have the same sign. But then minus 6x, so that negative middle term means if they have the same sign, they've both got to be negative, so you get a negative middle term. So both negative. There is only one possible option for this, right? Because pairs of factors of 5, they're either 5 and 1 or -5 and -1. So really here, I guess I could just write this as your only possible pair would be -5 with -1, which does work, right? If you add those together, you get -6, so we're all good, right? And then you would just write this as -1 times x minus 5 times x minus 1, and then that is what the factorization would look like. So either like that, or sometimes maybe you see it where it just has the negative out front. So one of those. I prefer, for whatever reason, having the -1 in there. I guess I like to write this in a more literal fashion. I suppose that's what that would mean. But a -1 out front or just a negative out front, they mean the same thing, right? 6 looks harder, and it's not. I guess that's really the point. Yes, there are two variables. It looks like you have to do more things, but think about how this would work with foiling, right? Basically what you're doing now is you're trying to find, if I just do this with a different color, you're still looking for an m and an n. It's just that now what you're doing is you're trying to make it look like this, where you're trying to have it be mu plus mv times mu plus nv. Right? So yeah, there's that extra variable, there's that v, but then you think if you FOIL that back out, then when you multiply the two last terms, you're going to get a v squared in it, and then you'll get that u times v in the middle term, because when you do the outer and the inner, with that multiplication, you're going to get a uv both times. So it looks like it's going to be harder, but really it's like what we've been doing. You just have to kind of tack a v onto the end of the two binomials, right? Just in the second terms. So it's not too bad. And strategically, we're still kind of doing the same stuff, where we're looking at this and we're going, all right, well, -12, that means that your m and n should have opposite signs, right? And then the -4, I guess I should write that as -12v squared and -4 uv. So the -4 uv, that's telling you that the negative has the larger absolute value. And then if we start thinking about our pairs that we could have, so they'd have to be pairs of factors of -12. So you could have -12 with 1, right? Because we got to have the negative having the larger absolute value. We could have -6 with 2, and I guess we could have -4 with 3, right? And that would be it. And then which one adds up correctly? The one in the middle, right? That adds up to -4. That's -11. That's -1. We want that one right there in the middle. So what does this look like when you factor it out? All right, what this is going to look like is it'll be u minus 6v times u plus 2v. And in this kind of situation, because, I mean, I'm really used to this, so I kind of see this and I go, that second variable doesn't really make things any harder. But I've done a million of these things. So if this is a thing where you haven't done a million of these things, it might still look kind of complicated with that extra variable in there. What I would say is, in order to get used to it, just do what you think you should do and then multiply it back out, right? And then if it works, if you get what you started with, then you got the right idea. And if it's slightly off, then you just have to tweak it a little bit, right? You think, oh, well, I put a V here, but I forgot to put one here. I got to put one here too, right? Maybe something like that. But yeah, ultimately, even having that extra variable in there, we're still doing what we were doing before. And then this also looks complicated, but it's not too bad because this has a greatest common factor that we can pull out. Because if you look at those coefficients, you think, wait a minute. Got a couple of 20s and a 40. Those are all divisible by 20. Yes, they are. And also, notice there's an x cubed, x squared, and x this time. So we could also factor out an x. So what we're ending up with here is that we have a greatest common factor of 20x. So the first thing we should do is factor that out. So if we factor out a 20x, then let's see, 20x times x squared would give us the 20x cubed. Then minus 20x times 2x would give us the 40x squared. And then 20x times 1 is 20x, right? So you end up here. So then for the thing that's inside the parentheses, the plus 1 would mean that the two factors have to have the same sign. And then the minus 2x means that they're both negative. Well, I think we're done because they're factors of 1. So the only pairs of factors of 1 are 1 and 1, or negative 1 and negative 1. And since they've both got to be negative, it's negative 1 and negative 1, right? That's your only option, and that does work, right? Negative 1 plus negative 1 is negative 2, so you'd get the correct middle term. So you'd have 20x times x minus 1 times another x minus 1. So you could write it that way, or you could sort of compress that a little because you got two x minus 1s multiplied in here. So you could write it as 20x times x minus 1 quantity squared, right? I guess that one's a little bit smaller in terms of like how many characters you're writing out. And this can happen, right? You can have repetition in here. There's nothing wrong with that. And actually, section 4.6 covers a lot of that stuff. But this is one where at the beginning it looks sort of intense because you got these big coefficients in here, but there's a greatest common factor. So this is just sort of a callback to where if that's a thing, which, I mean, to go back, like with number 1 through number 6, the leading coefficient is 1, or I guess in this case, negative 1, every single time. And when that happens, there's nothing to factor out. But then here, when it's not a 1, you probably want that to be your first step, just to check and be like, can I factor anything out of this? And here we could. All right, the next thing is, what if the leading coefficient's not a 1? This gets more complicated then, because there's more stuff that you have to worry about, and it's generally going to be a little bit longer, and these tend to be a little bit more difficult, just because there are more options. That's kind of what happens. And I wrote down every single thought that was in my head in this thing here. So for trial and error, because basically you have two options. One of them would be trial and error, where then what you do is you try different pairs of factors of A and C. Because now if A is not 1, then it's not just going to be a 1 with a 1 like it has been before, right? Because whenever we have an x squared, we go, oh, that's just a 1x with another 1x. And we always just write it as x here, x there, and just go, right? But then it's like, well, what if it's a 4x squared now? Then it could be a 2x with another 2x, or it could be a 4x with an x, right? So you got different pairs of factors. So you have different pairs of factors of A and C, and you could try, different combinations until you get the correct middle term when you multiply the binomials out. So like when you FOIL them out. And depending on how many pairs of factors A and C have, this could be kind of short and it could be kind of long. When it's short, well, I guess when it would be the shortest would be if A and C were both prime. Because then they don't have a lot of factors, right? It's just that number and 1. And then you get through it really fast because there just aren't that many different things you can do. But then you go, well, like what if A was like 24, which has a whole bunch of different factors. And then C was something like 60. Like, that's going to take a long time, potentially, unless you get lucky. But what I've got here, so this one that I said doesn't take very long, yeah, that's because 3, the coefficient of the x squared, so our leading coefficient, that's a prime. So like when you factor it, it would have to be with a 3x and an x, like it says there. And then 22 doesn't have a lot of pairs of factors, right? It's 22 and 1, and then 11 and 2, and that's it. So then for negative 22, you go, well, then there are 4 pairs because one of those has got to be positive and one's got to be negative, right? It's still, you got that negative constant at the end, you got to have opposite signs, right? So it's either negative 22 with a 1 or negative 1 with a 22, and then same thing with the 11 and the 2. One of those has got to be negative, one's got to be positive. And then you have to consider the positioning of the factors because sometimes you're multiplying by 3 and sometimes you're multiplying by 1. So like you could have the negative 11 in the first one and the 2 in the second one. But then if that doesn't work, maybe you also have to consider the 2 in the first one, the negative 11 in the second one. But you won't have to check all 8 because there are going to be some things that you can throw away just by eyeballing them. Like for example, it's not going to be a 1 in the first one and a negative 22 here because then when you FOILed it, just think about what happens to the middle term. Negative 22 times 3x is negative 66x. And then you have a plus x, that's negative 65, right? That's a huge negative. That's not going to work with what we've got going on here. So that always kind of happens where there are ones where even before you do them, before you like try multiplying them out, you can look at them and go, no, there's no way the middle term is going to work. And then you just don't focus on those and focus on the ones where the middle term might work out. So that one, I mean, it's not too bad. I think at most you would have to check like 3 or 4. It's not bad. And then on the other hand, factoring this could be a beast if you're going to do it by trial and error. Because for the 12x squared, you go, well, could be 12x with an x, could be 6x with a 2x, could be 4x with a 3x. That's a lot of possibilities there, especially because then you say, well, what about pairs of factors of 40? 40 and 1, 20 and 2, 10 and 4, 8 and 5, right? And then it's a negative 40. So then you have to consider like, well, it could be a negative 8 with a 5 or an 8 with a negative 5. And then you'd have to consider the possible orders, right? Because there are going to be 2 orders for each one. So there are a lot of things that could happen here. But some of those you could eliminate pretty fast. So that's, and just because there are going to be ones where the middle term would be so far off and you'd be able to see it right away, you could just kind of throw them out. But you're still going to end up with a ton of things to do. So I think basically this is one where maybe you'd be better off doing it a different way. So the other way would be something like this. Oh, I forgot to say this. If you're going to do this by trial and error, this is actually a big thing, and it took me a long time when I was learning how to do this to figure this out, or like to catch this when it was happening. There are some possibilities that you don't have to check because 12x squared minus 17x minus 40 doesn't have a common factor. But this, you could factor a 2 out of. So it can't work, right? Because then whatever trinomial you're going to get would also have that common factor of 2, and that's clearly wrong, right? That's not what we have in this original trinomial. So this second point here, this is actually a big deal. I meant to kind of stress that because that eliminates a bunch of choices usually, right? Because you couldn't have a binomial where both coefficients were even, right? Like that can't be part of the factorization because then that creates a situation where there's a common factor, and we know there shouldn't be one. All right, so the other method, because like this is so long, where if you look at this and you think, I would rather do something a little bit shorter, because what if you have to check like 12 different things? Like that would take forever. The other way to do it, our book calls it grouping. I've heard people call it the rainbow method, or I've heard people call it the AC method. I call it the rainbow method because what you can do, so let's see, was it with a minus 40? Yeah. Okay, so like with the 12x squared minus 17x minus 40, I call it the rainbow method because you make the rainbow like that from the beginning to the end. And then you multiply those two numbers together, right? Because like it said, that's what you do. You multiply A and C together. and you find a pair of factors of a times c that would add up to b. And then what you can do is you can rewrite that middle term. So like it says here, you can rewrite b times x as mx plus nx if m and n are those factors. And then you end up with a 4-term polynomial that then you can factor by grouping like we were doing in the last section. So as far as the strategy goes, both methods are always going to work, although sometimes one would be faster than another. Certainly if the leading coefficient is a 1, so like if you just have an x squared plus, whatever times x plus some constant, if the leading coefficient's a 1, I wouldn't bother with the rainbow method. I think it would be too long. I think you can get it faster without that. But if your leading coefficient's not a 1, it depends. Like, it's kind of a gray area. I would say if A and C are both prime, just go for it with trial and error because you just don't have very many options. You'll probably get it really fast. But then the more factors A and C have, the more things you would potentially have to check. So I don't know if there's like a threshold where I'd say if it's more complicated than this, then I would be doing it with the rainbow method. But I just kind of eyeball it. And if I can't think of a couple of things to do right away, like with this one, with the 12x squared and then ending with the minus 40, I would look at that and go, there are a ton of possible options. I'm going to the rainbow method, right? So I don't know if there's one thing where, like this is the threshold for when you go past it. Like this is where it's the rainbow method, like I said before. But I think that varies from person to person too. But they're always both going to work. It's just that sometimes one's going to be faster. All right, so then factoring those polynomials that are there that I just kind of wrote into those examples. So this first one, so the 3x squared plus 31x minus 22. Let's say if we were going to do that one by trial and error. We can. So we can still use the fact that if the constant is negative, then that means that m and n, so to speak, have to have opposite signs. So we can still use that. And we can still say negative 22 would lead to opposite signs. And then we basically just have to start trying stuff, right? So let's say if we tried, and we just need pairs of factors of negative 22. And this doesn't always work, but it seems to work a lot to kind of work from inside out, unless you have some crazy looking middle term. What I mean from inside out is my middle term is big, but it's not like insanely huge. So I would think that it's probably not going to be like the extreme pairs of factors, like negative 22 with 1. I wouldn't be thinking that. I'd be thinking like maybe an 11 with a negative 2 or a negative 11 with a 2. And we'll start there and see what happens. So those are closer together, the negative 11 and the 2, right? Or I guess 11s and 2s are closer together than 22s and 1s, right? So I tend to work that way, like closer to farther in terms of the two numbers in the pair. But that, I guess, is kind of just a preference, but it does tend to work out better. So let me just try this. Let's say 3x minus 11 times x plus 2. Because we know we got to have a 3x and an x, right? So let's try this. If we multiply this out, what are we going to get? We're going to get 3x squared, then plus 6x minus 11x minus 22. Okay, that didn't work, right? Because we didn't get the right middle term. We got a minus 5x, we're supposed to get a plus 31. Okay, let's just put these in the opposite spots. So like 3x plus 2 times x minus 11. Where's that going to get us? All right, so there we multiply out. We're going to get a 3x squared minus 33x plus 2x minus 22. This doesn't work, but it's almost right. So I guess I'm just going to highlight that by making it red. Almost, right? Because if you look at what we got going on here, we're going to get a negative 31 and we're supposed to get a positive 31. Here's another technique. When this happens, when you're almost right, but you're just getting the wrong sign, the middle term, just flip the signs here. Because if you flip these two signs, that's going to give you the same first term and last term, but when you FOIL, it'll flip the two signs on the O and the I, right, on the outer and the inner, and that'll give you the opposite sign in the middle term. So that's what I'm going to do here. I'm just going to flip the signs and say it's 3x minus 2 times x plus 11, and let's see what we get. And if we multiply that out, we are going to get 3x squared plus 33x minus 2x minus 22. Good. That's a plus 31. We got it. So that means that this right here is the answer, because it multiplied out correctly. It gave us what we wanted. So good, right? We got our 31x right there. Okay. This one, if you just for comparison's sake, like what if you wanted to do this with the rainbow method? All right, so let me just kind of section this off. So make that blue. All right, so we were going to do the same one, but with the rainbow method. All right, so what I would do is, so we got the 3x squared plus 31x minus 22. We are going to get the same answer, but I just wanted to show you how this goes. So I guess I'll make the rainbow a different color. I'll make a red rainbow. And there's our rainbow, right? And then what you do is you multiply those numbers together, right? So you'd say a times c would be 3 times negative 22, which is negative 66, right? And then we want factors of negative 66 that sum to 31. And what we're going to end up with is, looks like 33 and negative 2. Right? And I guess you could cycle through them and check, right? Because then you could be like, well, let's see. It's got to add up to a positive. So then that would mean that one's going to be positive, one's going to be negative, but the positive one has to have the bigger absolute value. And if you start thinking of things like, let's see, 11 and negative 6, no, that adds up to 5. That doesn't work. Or 22 and negative 3, like that adds up to 19. That doesn't quite work. All right, so you'd get there if you had to think about it for a minute, but you'd get there pretty quick. And then once you have this, so this is the key right here, because then what happens is that you can rewrite the trinomial as 3x squared plus 33x. Uh-oh, can't write. 33x minus 2x and then minus 22. So notice what I did compared to the original trinomial. I just broke up that 31x into 33x minus 2x. But then this you could factor by grouping. And you could say, well, then this is, so if I group the first two and the last two, so 3x squared plus 33x, and then that negative needs to go with that too. So plus negative 2x minus 22. And then here you could factor out a 3x. So 3x times x plus 11. And then here you could factor out a negative 2. So negative 2 times x plus 11, right? Since negative 2 times 11 will give you the negative 22. And then you can factor out that x plus 11. And what you're going to be left with is 3x plus negative 2, which most people just call 3x minus 2. And then, oh, look, it's the exact same answer. So yeah, it works, right? So either way would be fine. With this particular one, like for me personally, I'd probably be doing the trial and error just because that 3 is prime and then the 22 doesn't have a lot of factors. But the rainbow method's not that long, right? I mean, it'll work. For that other one, I'm going right to the rainbow method. So hope I got enough space. I think I do. But let's see. For the other one, we've got... so I'm going right to the rainbow here. So rainbow method. And we've got 12x squared minus 17x minus 40. And if we're going to do the rainbow, I guess I can draw another rainbow. So 12 to the 40. All right, this is a big number. Looks like it's going to be negative 480, All right, so AC is going to be 12 times negative 40, which is negative 480, right? Since 12 times 4 is 48, that would have to be true. So then we need and I guess I should put pair of factors. So we need a pair of factors of negative 480 that sum to the coefficient of the middle term. So they sum to negative 17. So I guess then we can try some stuff, right? And you say, well, how can you get a negative 480? And remember, they got to add up to a negative. So they're going to be opposite signs to get the negative 480. But then the negative's got to have the bigger absolute value because they add up to a negative number. The first one I would think of, even though it's clearly not going to work, would be negative 48 and 10. Now you multiply those together, you get negative 480. But they add up to negative 38. Doesn't work. Okay, maybe negative 24 and 20, right? Since 24 times 2 is 48. That's going to add up to negative 4. That doesn't work. So it should be in between these, right? And then you go, well, does 15 work? Actually, it does. Negative 32 times 15, that is actually going to be negative 480. So think about it this way. Like 32 times 10 is 320. And then 32 times 5 is another 160. So yeah, it's going to add up correctly. You get negative 17. That is what you want. And then we can do it, right? So we're going to take this pair and we're going to rewrite the trinomial as 12x squared minus 32x plus 15x minus 40. And then we're going to group first two and last two. So 12x squared minus 32x, and then plus 15x minus 40. And then let's see, we could factor a 4x out of this. So factoring out the 4x, we'd be left with 3x and then minus 8. Here it looks like you'd factor out a 5. And then you'd be left with 3x minus 8. And it looks like we got it, right? 4x plus 5 times 3x minus 8, and that's the answer. If you do this one by trial and error, maybe you'll get lucky and you'll get the 4x plus 5 times 3x minus 8 relatively quickly, but maybe not. Maybe it takes a long time. So this is one because the 12 and the 40 both have a lot of factors. I think I would go right to the rainbow method first. All right, now for a bunch of examples where you would have a leading coefficient that's not 1. Okay, so like for this, plus 10 at the end. So I'm still thinking if you get that plus 10, then your two integers that end up in your binomials, they must have the same sign, but then you're getting a positive middle term, so that plus 9x means that they're going to be both positive. And there aren't really any options as far as what you're going to do for the leading terms of your two binomials. It's got to be 2x and x, right? Since 2x is, or since 2 is prime, right? Rather, right? So it's got to be that. And you could start checking things. So you think, okay, well, what are the pairs of factors here? So like our pairs, well, you could have, I guess, 2 and 5, and you could have 1 and 10, but you'd have to consider both orders, right? So let's say we go 2 and 5. This isn't going to work because this has a common factor, right? So this one, like right off the bat, you could say right here, there's a common factor. So you automatically know that doesn't work, right? Because this doesn't, the 2x squared plus 9x plus 10 doesn't have a common factor. You could multiply it out and it won't work, right? You're going to get, let's see, 10x, you're going to get a 12x instead of a 9x. So I guess even if you didn't catch that, it's still not going to work. Then you say, okay, well, that didn't work. What if we try the opposite order? Like put the 5 on the left and the 2 on the right. All right, so 2x plus 5 times x plus 2. Is that one going to work? Let's see. We're going to get 2x squared plus 4x plus 5x plus 10. Yep, because that's a 9x right there in the middle, right? So we got the thing that we were supposed to. And so there's the answer, right? So I guess I can box that one in. Right there is our factorization. Okay, how about the next one? This time we've got a negative 15 as our constant. So that negative 15, that tells you that we should have opposite signs. This is another one I'm not going to use the rainbow method with because of the 7. Right, that's 7a squared. 7 is prime. Right, so there aren't any real options there. It's 7a in one of the binomials and a in the other. There's nothing else you can do. So I'm thinking we got a 7a here, and we got an a here, and then other than that, like because there's a 7 and a 1 being multiplied in with the middle terms, we can't really say anything about like the negative and the positive constants that are going in here, like which one has a bigger absolute value. We just have to start trying stuff. Right, so our pairs, you say, well, we could have like negative 5 with 3, or we could have a 5 with a negative 3. We could have those in the reverse order, and then I guess we could have a negative 15 with a 1 or a 15 with a negative 1. So I guess let's try the negative 5 with the 3, right? And if we multiply this out, it's going to be 7a squared plus 21a minus 5a minus 15. Ooh, got it in one shot, right? This works, right? Because this is a 16a. We're done. Sometimes you'll get it on the first try, right? So, got it. All right, so that one we got. What about this? Let's see. This would be another one where maybe if you look at it and think, you know, well, should we be going to the rainbow method here? Maybe, but because this is a plus, you know, they have to have the same sign, that actually cuts down a lot of possibilities. This one I would say is borderline. If you wanted to multiply 15 and 8 together and go, well, that's 120, we need a pair of factors of 120, they're going to add up to negative 22. You can do it like that. And it looks like it would be negative 10 and negative 12, right? But let's see. I think this is one I would still, because the 8 is positive, that would mean that you'd have to have the same sign and with the two constants, and so that looks terrible. Let me just erase this and start over. All right, so we have the plus 8, which that means that you have to have the same sign, but then in order to get that negative 22, if they're the same sign, they both have to be negative. So that still works. If they have the same sign, you still get that extra piece from the middle term, even though you don't have a coefficient of 1 of the y squared. All right, so then what are our pairs? Well, if they're both negative, it's either going to be negative 4 with negative 2 or negative 8 with negative 1. At most, you would have to check 4 things here. Well, unless it's the 15 with the 1 with the y's. But I would think, so I guess these are our C pairs. And we're also going to have A pairs because we could have 5y with 3y to get the 15y, or we could have 15y with y. But this is another one where you probably want to work inside out. It's much more likely that it's going to be the 5y and the 3y, just because the middle term's not something completely insane. If the middle term was like negative 60 or 70 something, then I'd be thinking about the 15, maybe. But I think generally you want to try the ones like the 5 and the 3 first. So let's see what happens if we have, so 5y minus 4 times 3y minus 2. Let's see what that's going to give us. So that'll give us 15y squared, then minus 10y, minus 12y. Oh, really? I didn't mean to get that one right on the first try. That was luck. Actually, I kind of thought it would end up working out a little bit differently there. Oops. I guess when this happens, you just go with it, right? So yeah, this will end up actually working out correctly. So that is the answer. Right? We're getting the middle term that we're supposed to, so don't look the gift horse in the mouth, as they say. Right? When you get it on the first try, I guess you just go with it. If this one, like I did not expect to get this one in one shot. I expected it to take 2 attempts, maybe 3. So, I mean, if you don't get it the first time, don't worry about it with these. If you're going to do it with trial and error, just expect to not get it the first time. And then when you do, then it feels good, right? I think that's the idea. You know, expect it to take like 3 times. Then if you get it the first time, then, right, then that feels great. So, yeah, we got that one right away. I didn't think we would, but there it is. And I guess if you were going to use the rainbow method, since I've got the space here, I could write this in. All right, so if you were going to use the rainbow method, so A times C would be 15 times 8, which is 120, and then your pair of factors of 120 that sum to negative 22. So if they're factors of 120, they'd have to have the same sign, but they're adding up to a negative, so they both got to be negative, right? And so your possibilities, I guess, would be things like, you know, negative 24 and negative 5, but that doesn't work because that adds up to negative 29, not negative 22. The one that actually works would be negative 10 and negative 12, right? And so let's just say, like, if you think about that one, and then you broke it up, you'd have 15y squared minus 10y minus 12y plus 8. And then if you grouped that, so 15y squared minus 10y, and then put that negative with the 12, so negative 12y plus 8. And then from there, let's see, you could factor a 5y out of that first group, and you're left with 3y minus 2. And then you could factor a negative 4 out of the second group, and you're left with a 3y minus 2. And you can see that this works, right? You're going to get 3y minus 2 times 5y minus 4. So yeah, either way, right? Either way is fine there. This one, I would look at that, and my first thought when I see that 36x squared is, oh no, right? Because that's a lot of options for x squared, right? Because you go, well, could be a 6x with a 6x, could be a 9x with a 4x, could be a 12x with a 3x, could be a 36x with an x, but look at this, 36, 33, 12. Those are all divisible by 3. So this is one where if you see something that looks a little awry, you go, well, wait, maybe there's a greatest common factor, because here there is, and you could factor out 3. So that is the first thing that we're going to do here, is we're going to factor out a 3, and we're going to be left with 12x squared minus 11x minus 4, it looks like. And then from there, we should be able to factor this thing. Let's see. Actually, this is typed wrong. I'm looking at this and I'm like, this doesn't work. This is actually supposed to be a 3. I'll have to go back and fix that. Yeah, that's what I wanted here. Because I'm looking at this and I'm thinking, this is not how this is supposed to go. All right, so then if that's a 3, then when you factor out the 3, then this is a 1. Okay, that makes more sense. Because then if we're going to try to factor this, there aren't too many options down here, right? You go, okay, they have to be different signs. So fine, one of them's a 1, the other one's a -1. The things that you'd have to worry about maybe would be, what about this, right? Because then you got to figure, like, well, you got to factor 12x squared minus 11x minus 1. Okay, well, for 12x squared, you could have a bunch of different options. You could have 6x with 2x, 4x with 3x, 12x with x, right? So you could try different things here, and you got to get that negative middle term. So what I would be doing is I would be trying to angle it. So in order to get that negative, you want it down here, right? You want it in the second one, so then that way it gets multiplied by the big coefficient here. So I'm going to do it like this. And let's see, this is not going to work properly because we're going to get 6x squared minus 6x plus 2x minus 1. So that doesn't work because we're getting a negative 4x as the middle term instead of a negative 11x. The 4 and the 3 is clearly the wrong direction because then the middle term is going to be too small, or it's going to be close to 0. But what if we did it like this? So 12x with x. And then I want to get a negative in the middle. So I got to put the negative here. So when we FOIL, that negative gets multiplied by the big x coefficient. And if we do that, then we're going to get, that's a 12, not a 6. This video is so long, I'm getting fatigued. So 12x squared minus 12x plus x minus 1. Good, right? That works because there's the negative 11x right there. All right, so then that means this factors as 3 times 12x plus 1 times x minus 1. And that is the answer. So I got to go back and fix that typo. So I guess if you print these out in advance, it'll probably be fixed on the thing that you print out. Hopefully. All right, then what about 12? Oh, looks like we've got a couple of variables again, right? Just like when we had that show up before. What I would say with 12, I think, this is one where I think I would just go ahead and use the rainbow. Right? I'd be looking at this and I'd think, I could probably get it if I fooled around with this a little, but I'm going to do the rainbow. So a times c here is just 6 times 6, which would be 36. And then we would need a pair of factors of 36 that sum to 13. And if you think of factors of 36, you go, well, 6 times 6 is 36, but that's not going to work, right? 6 and 6, when you add them together, that's 12. Nope. Anything else, like 12 times 3, that's 15 when you add them together, that doesn't work. 9 times 4, that's 13 when you add them together. So that's what we're going to use, right? We're going to use the 9 and the 4, because then we can write that trinomial up there as 6x squared plus 9xt plus 4xt plus 6t squared. And then we can group. So we'd have 6x squared and 9xt in the first group. And then we're going to have 4xt and 6t squared in the second group. And then let's see, we could factor a 3x out of this first part. So 3x times 2x plus 3t, it looks like, right? 3 times 3 would give you the 9. X times t is xt. So yeah. And then this one down here, we could factor a 2 out of the coefficients. They're both even. We could factor a t out of both terms. It looks like that's it. So 2t times 2x would give you 4xt, right? 2 times 2 is the 4, t times x, xt. And then 2t times 3t would be 6t squared. So then that means what we're going to get is 3x plus 2t times 2x plus 3t. All right. So we had one with a couple of variables, but we got through it. All right, next, 13. 13 has got things that we can factor out, it looks like. So if we look at what we've got there, we've got all terms that are even, or all coefficients that are even, right? 30, 16, 2. And then you look at the powers of a and the powers of b, you go, wait a minute. All the b's are b squareds. And then a's are a squared and up. So we can factor a greatest common factor out of this. All right, so our GCF looks like it would be 2 for the coefficients, and then an a squared for the a's, right? Because we had an a to the fourth, a to the third, a squared. And then there's a b squared in all three of those, so we could factor that out too. All right, so if we're going to rewrite this, we would have 2a squared b squared times, let's see, from the first term, we'd be left with a 15a squared, right? Since a squared times a squared is a to the fourth. And then that b squared is already taken care of. All right, then minus 8a, right? And then plus 1. All right, this isn't too bad, right? Because from that plus 1, so the plus 1, they have to have the same sign. So they're either both positive or both negative, and negative in the middle, so that negative 8a is both negative. There's only one option, which is they've both got to be negative 1, right? Because they're factors of 1. The only possible options are 1 and 1 or negative 1 and negative 1. If they both got to be negative, they both got to be negative 1. So what we can do with this is we can say, well, then we got 2a squared b squared times, and then I guess it comes down to, well, do you use 5a and 3a, or do you use 15a and a? Well, we know we got to get that negative 8 in the middle, and if you think, well, 5 plus 3 is 8, that's the right idea. Because if we have 5a minus 1 times 3a minus 1, that's going to do it, right? Because if you multiplied this back out, you're going to end up with 15a squared minus 5a minus 3a plus 1 minus 5 minus 3 minus 8. So yeah, looks like we got it. So that's another one where it looks crazy at the beginning, but if you factor out the greatest common factor, it ends up not really being that bad. All right, let's see, next, how to factor by substitution. Okay, this is also in here because it goes along very nicely with factoring trinomials. This is when you have things that look like trinomials, but there's something a little wrong with them, right? Like this, you look at it and you go, well, I mean, it's a trinomial, but it's not a quadratic, right? Because you got the fourth and the squared instead of a squared and x to the first, right? That's almost what we want, but not quite. And then so is this, because you go, well, this kind of looks like what we were doing. If we had n's instead of n plus 1s, it would look exactly like what we were doing. So the general idea is you can write the expression like this, where it's constant times something squared plus another constant times the same something plus c. Then you can factor by substitution. And by substitution, that just means you use a placeholder. You say, like, let u be n plus 1 or let u be x squared, and you do it like that. Our book uses a smiley face instead of a square, but the equation editor doesn't have smiley faces, so the square is the best looking thing that I could come up with. All right, well, here, like, this almost looks right, but what you want to do with this is if you let u, let's say, you just need some kind of placeholder. The common one to use is u for whatever reason, but we'll just say, what if u is x squared? Right, because what we've got right now, so x to the fourth plus 5x squared plus 6, you could say, well, really that's x squared squared plus 5x squared plus 6. So then if we do the replacement, which is going to happen right here, this is where we're going to sub. We're going to have u squared plus 5u plus 6. So basically I just stuck u's in where the x squareds were. But then this is a thing that we can factor, right? Because for this right here, you can say, well, plus 6, they're going to be the same sign. And then plus 5u, to get a positive middle term, they would have to be both positive. And then you go, okay, well, factors of 6, it's either 6 with 1 or 3 with 2. And to get the middle term of 5, it's 3 with 2. Right? This has got a coefficient of 1 with the u squared. So this is the easier kind of factoring. So you'd end up with u plus 2 times u plus 3, or u plus 3 times u plus 2, right? Either way. But then you have to back sub. So your final answer should have x's in it, not u's, because you started off with an expression with x's in it. So u is x squared, so you'd have x squared plus 2 times x squared plus 3. That's actually the final answer. So right here is where you back sub. Right? If you sub, then later on to get the final answer, you have to undo it. Right? You have to back sub. So you end up with an answer in terms of the same variable that you started out with. So there we go. Right? That's the final answer there. Okay. Then the other one with the n plus 1s, you would do the same thing, right? Or you'd go, well, if we had u be n plus 1, we can make that kind of substitution. So we'll just say let u equal n plus 1. Then what's going to happen is we're going to go from 2 times n plus 1 quantity squared minus 15 times n plus 1 plus 13. And if we do the sub, so that's going to happen right here, we're going to end up with 2u squared minus 15u plus 13. If you wanted to use the rainbow method here, you could, but there are so few options that I think I would just go for it with trial and error, because 2 and 13 are both prime. So you know you got to get 2u in one of the binomials and u in the other because of the 2u squared. But then with the plus 13, that means they're going to be the same sign, but it's a negative middle term, so negative 15u, that's going to mean that they're both negative. And they're factors of 13. There's only one option. They're negative. It's negative 13 with negative 1, right? So your only pair is negative 13 with negative 1. And then you just have to figure out, well, where do they go? Do you put the negative 13 first, or do you put the negative 1 first? Well, you got to get a negative 15 in the middle, right? So then if you put the negative 13 here and the negative 1 here, it looks like that'll do it, right? So you get a negative 13, then minus 2. So it looks like it's this, right? And then you got to back substitute. So then if we're going to do that, then we're going to have 2 times, or I actually need a parenthesis out there, 2 times n plus 1 minus 13 times n plus 1 minus 1, right? So then here, this is the back substitution. And then, so what are we going to get? We're going to get 2n plus 2 minus 13, if I distribute the 2. And then here, n plus 1 minus 1, that's just n, right? So what do we get? We get 2n minus 11 times n. And I guess really around the n, you don't even really need those parentheses. But that's the answer. And it doesn't really look that way when you look at the original expression that we have up here. But that's because that thing's not multiplied all the way out, right? Like if you distribute the 15, you distribute the negative, and you square this and distribute the 2, then what you would end up with is actually an expression that has no constant term, right? It can't if we were able to factor out an n. All right, last one. This last one here is sort of a gag. It looks way worse than it is, and I guess that's part of the point. This is another one where I get to harp on factor out the greatest common factor, because these 3 products here, they each have an x minus 2 in them, so we could actually factor that out. and 15, 15, 30. Those three numbers are all multiples of 15, right? So what we could do with this, our GCF is 15 times x minus 2. So then we're going to factor that out. We're going to have 15 times x minus 2, and then we're going to have what's left over. I guess to make it more distinct, I'll put it in brackets. So we'd have x squared from the first term minus x from the second, right? Because the 15 times x minus 2 is already factored out. And then minus 2. Okay, well, factoring this isn't so bad, right? Because then you need a pair of factors of negative 2 that add up to negative 1. Well, I guess for what's inside there, if you want to kind of analyze everything, the negative 2 would mean that you have opposite signs, and then the negative x would mean that the negative has the larger absolute value, right? We can play this game again because the coefficient of x squared is 1, right? So then that would tell you that. I'm just having the negative middle term. But then there's only one option, right? Because the only factors of 2 are 2 and 1. So for negative 2, it's either negative 2 with 1 or 1 with negative, or 2 with negative 1. You need the option where the negative has the bigger absolute value. So it's got to be x minus 2 times x plus 1, right? So then here, like, your only pair would be negative 2 with 1, right? That's the only one that satisfies both of these things. So you get here and you go, okay, well, that looks like the answer. So you could either write it like this, or you could clean it up a little bit. So like that, or because you have two x minus 2's in there, you could write it as 15 times x minus 2 quantity squared times x plus 1. Like that, right? Either way. This last one's probably better. I think that's more conventional. But the main thing is getting to this point, is to seeing, like, this thing looks insane, but there's a lot that you can factor out right away as part of the greatest common factor. And then the thing that you're left with, the x squared minus x minus 2, that is not insane, right? Like, that's one that's really doable. So, yeah, always remember, look for the greatest common factor first, just in case, right? Because if there is one, it's going to make things go a lot smoother. And I think that's really what the point of this example is supposed to be.